So in the previous video we looked at MNIST binary classification. So just a brief recap of what we did. So there was a MNIST data set and we converted this problem into a binary classification problem where we looked at how to import data and looked at the data properties, and when we looked at a couple of models, HGD classifier model and never 5 naive model. Then we looked at a few performance metrics and finally looked at error analysis. So the structure is shown here, but in this particular session we are going to look into MNIST multi-class classification. Instead of looking at whether it was 5 or not, here we are trying to recognize what each image means, which number it represents. So briefly we are going to, the structure of this particular notebook is given here. In particular we are going to focus mostly on this section, which is the modeling section, 1 versus 1 versus 1 versus rest and tree models. Also look at feature importance and how to use do error analysis, confusion matrix, and how to look at the data which are throwing errors, and also look at what are the next steps. So the configurations, as in the previous video, I am setting up a path where I have couple of utility paths. If I'm routinely using the same functions, I'm placing them in couple of these, but in this particular notebook I'm not going to use. But if you want to include your own utilities, you can definitely use this particular code to add to your path. And then the folder structure is, there is a project folder called MNIST, and then in that I'm creating data folder, notebooks folder and images folder. To import your data you can use this fetch OpenML, but because this is a big data set, I am importing only once and then dumping that as a pickle file locally so that I can load it whenever I want, or if I am rerunning this notebook several times, this load is going to be easier. And then finally here I downloaded the data into X and Y variables, and we looked at the properties of this one. There is no missing data, so no need to worry. And if you convert these pixel values into an image, this is how it looks like. It's a 28 by 28 image, and each of these pixel values are represented here, and you can see it's a 0 to 25. If you look at the properties, the maximum value, it goes to 254, 255 and so on. If you want to look at some instances, here is some code that I have written, and it's showing few numbers. We're going to use the same code to do error analysis later. So finally there are 70,000 records, but I'm using 20,000 to do for training, because it will take a long time to run all 70,000 instances I'm using, but ideally you could use a bigger proportion, let's say 60,000 for training and 10,000 for testing. So for multi-class classification, the difference between binary class and multi-class is there are more than 2 classes here. In this case there are 10 classes, 0, 1, 2, 3, 4 and 9, up to 9, and we are going to use mainly 3 ways of doing multi-class classifications. So one is 1 versus rest, so where we take one number and we, for example, if you are trying to predict 1, we are going to build a model 1, and then everything that's 1 is going to be yes, and everything that's not 1 is going to be no. So we create a 10 different data sets, and then we are going to run 10 different binary classifying models, and then we score each of those models. The one that has the best score is going to win that contest, and that will be the final result. So the other one is 1 versus 1. In this case you are testing 1 versus any other image, like other number, for example 1 versus 2, 1 versus 3, 1 versus 4, and so on. So you are going to create 45 models, and then you are going to see which of those in all of those 45, which one's the best. For example, if we let's say we score 6, we look at 5 and we score against all other numbers. If it say wins it 6 times, whereas if it take 3, it wins against all others 8 times, then definitely 3 wins, and that particular image is going to be 3. Finally, random forest classifier. This one we don't have to do either 1 versus 1 or 1 versus rest. It automatically can identify which particular class it belongs to. You don't have to convert it to binary problem to solve it. So these are the 3 main approaches that every people take. So we'll first try 1 versus rest. So 1 versus rest by default, sklearn actually does this by default. You don't have to do anything. sklearn takes this as the default option and run through it. So SGD classifier, if you just specify any classifier and run through it, this is going to run 1 versus rest. So in this case, for example, there are the number of classes are described here, 0 to 9, and then the score. If you take one example, I took the first digit here from here, and I'm trying to score. You can get the scores for this particular instance by calling this decision function, and you can see the scores are here, and the one that has the maximum score, in this case I think 5 has the maximum score, so that 5 becomes 0, 1, 2, 3, 4, 5. So this one has the lowest number, which is the highest value, so that becomes the maximum value. You can either get it as a argmax, or you can get it from the code directly by calling in this case I'm calling argmax, and that will be the digit that we are predicting. Maximum is 5. So you can see that there are 10 scores, which means there are 10 models. The other one is 1 versus 1. So to implement this, we need to in a way force our model to go approach this way. So we import 1 versus 1 classifier, and we are forcing the SGD classifier to go through this 1 versus 1 classifier, and we are then fitting x train and xy. So you can see the number of estimators for this particular 1 versus 1 classifier is 45, right? So if you do the prediction of that particular first digit, it's actually saying 5, and then I'm just printing the first 2 estimators. It's each of the estimator, first 2 are the 45. Each of the estimator is essentially a HD classifier with a random state, and then so here I'm using the tree model, which is the random forest classifier, and simply in this case you can, instead of generating the scores, you can actually get a probability directly, and here the probability is highest for 5, which is 0.84. So the prediction naturally is 5. So far it's all clear. I think the concepts are in this particular scenario, it's just 3, 1 versus rest and 1 versus 1 classifier, and then the random classifier. Each of them serves the same purpose, but the amount of data it used to estimate are going to be slightly different. In 1 versus 1, the amount of data is going to be just the portion of the data. Like if you are comparing 1 versus 2, it's only the portion that has 1 and 2, and it ignores the rest of the data. So the model will run fast for this. Each model will be run very fast, right? But the number of models are going to be many, like 45 models. Whereas here it's using 1 versus rest, it's using entirety of the data set, and random forest classifier also uses entirety of data set. So it's in a way there is a little bit of trade-off in terms of number of models you are running versus amount of data you are using when you are choosing 1 versus 1 and 1 versus rest. So finally, to understand where we are going wrong, we can simply print out a confusion matrix. Here you can see that the diagonals have a bigger number, which means the model is actually doing a decent job. The prediction accuracy here for this model is about 0.87 or so. So the numbers I did plot it here. So you can see the accuracy is about 0.88, 0.86 and so on. And I'm using the train prediction values and building a confusion matrix by feeding in y train prediction. So this particular matrix is the confusion matrix, and pictorially I can draw a heat map, and you can see the heat map represented here. You can see the majority are classifying well, but there are certain rows. For example, this particular column is not doing that well. Maybe even this 9 is not doing that well, because 9 is being classified for a lot of times, and so on. So to get which of the numbers are misrepresented, we can do simply do a calculation where we can make this diagonal 0 and rest of them as a percentage. So you can see that the biggest percentage is here for 9%, where 5 is being classified as 8, and also 9 is being classified as 4, 9 is being classified as 7, and so on. So we can look at couple of instances. So I wrote couple of functions to plot specific errors, but the way to generate that error data is the actual values and predicted values are put into a data frame, and I am selecting the ones. For example, if I want to look at 5 and 8, I'm selecting actual is equal to 5 and then predicted is equal to 8, and this is the data frame I have. Once I have this data frame, I can take some instances and the IDs and then plot them here. So this is what. So these instances, for some reason, the algorithm thinks that the 5 is actually 8. Maybe some of them looks like 8, and some of them have very bold image for 5, and for this one actually goes beyond the image, so it doesn't have complete value. This one looks like a 5, so maybe the algorithm is getting confused between 8 and 5. So this is another instance where the algorithm, the actual value is 2, but it thinks it's a 4. You can see that this one is actually represent a 4 written in a slightly different way. In some instances, people can write 4 as this way as well, so it's natural. I think the algorithm is genuinely not able to distinguish between 2 and 4. So these are the cases where we have. So this helps us understand where we are going wrong. And the other one is 2 and 8, and when 2 is being understood as 8, this is how the data is represented. So you can see that the third image 2 is represented, looks more or less like 8. If you give it a human, probably he might think a little bit before saying it's actually 2. So this is how you do an error analysis. You take some instances where it's going wrong from confusion matrix, and you plot them and try to understand why something is wrong. Sometimes it's going to be very obvious. Maybe the training data is wrong, and if the labeling was wrong, so you immediately can catch those things here and you can correct for that. So the other thing that we are going to look at is feature importance, because there are 28 times 28, 786 variables. It's not so easy. Even if you come up with 5 or 6, there are many image pixel values that are going to be important in this image, right? So it's not that meaningful, but we can still do look at the map of which of them pixels are important. So you can see here, these are all the pixels that are important. You can do a random classifier and get feature importance, and then you can plot along this one. So this plot digit, there is simple code that was written here, and that can help us plot digit. So this will show each of the pixel value, and you can see that the ones in the center are most important, and the ones on the edges are not at all important, and then ones in the middle are sometimes important, sometimes not. So it does make sense on what which pixels are more important. So in a way, if you trim a little bit, the algorithm will probably still be able to recognize what this digit is going to be. So few more things in any running. So we just ran some models, but we did not really explore the parameter space. So in order to explore parameter space, we can use grid search CV, and here is an example where number of estimators are between 200 to 500 maximum features. So because we have 780, I'm exploring anywhere from 300 to 600. and then the depth is 10 to 20. I'm not sure if this is the maximum, you can probably have more, but this code actually takes a long time to run. So one way to reduce the amount of time is to reduce the amount of training data that you are feeding in. It's a fine balance. Not sure, because if you reduce the amount of data, you might miss some valuable information. So if you have time, you can run with maximum amount of data possible. So in this case, I have been running it for almost half an hour and still running. Finally, for if you want to productionize this, and if you can dump the forest this classifier as a forest model.pickle, and if you want to load it for future use, you can just load it from Python and run it. So we pretty much covered, just to go through this, we covered what configurations are there, and then how to import the data, and then split the data, and then we finally looked at multi-class, one versus rest and one versus one, and then random classifier. We also looked into error analysis and feature importance, and then how to do grid search, so which is currently being run, and for production purposes we can save the model and use it later as a pickle file, and the code is simply this job ripped up down. And there are some things that we can still think about what can be done more on this model. So how can I improve the model? So we are still exploring the feature space, but XGBoost, a neural network model, can do wonders on these kind of problems where there's a lot of data. So those are some venues to explore, which we did not. And then training error versus testing error. Right, so this is also that we did not look, but this can also be looked. We train the model and see how much error the amount of time it takes to train, and then the error that we are getting on the test set for different parameters. We can plot these values. Also, we can generate additional data, so we can transform the current image. For example, you can take something like this, let's say this 5, and we can shift a little bit, like change orientation. We can change the orientation of 5 by, let's say, 5 degrees left side and 5 degrees the right side, and then create another image. Right? So that becomes input data, and so that can sometimes help improve the model. So feature engineering, again, we can do some feature engineering which we did not do here. So for example, if we take a 28 by 28 cell, we can split into maybe a 4 by 4 grid, and then you compute the number of pixels or the sum of the pixel values, and we can use that as a feature. Or you can also do the distance from the center as one of the feature. That can also be useful. Then there is neural network models like CNN. Convolutional neural networks are really shown to work well on image data, and that's something that can also be explored to figure out how the model performs on this. So with this, I conclude MNIST multi-class classification problem. I think in the next one I can look into multi-layer